Thank you, Eduardo, for a very kind introduction. Good afternoon. It's my pleasure to be here and share with you my research interest. Today, I'm going to tell you how, using chemistry, can we make our production, chemical reaction more sustainable. I'm sure that everyone here is aware about progressive environment degradation. Climate is warming, water and air are polluted, trash are everywhere. The huge amount of all of this trash is plastic. When I say plastic, I mean polymers. Polymers are everywhere. Polymers are in the screen, in this pointer. Polymers are everything which we are producing. 70 years ago, in 1950, we produced 1.5 million of tons of plastic. And year by year, we get even better and better and better to get in 2021 nearly 400 million of tons of plastic. We produce 400 million of tons of plastic per year. And from this huge amount, only 9% of plastic is used by us again. Only 9% is recyclable. With 91%, we simply don't know what to do. What we do now, we are collecting them on specific landfills, and probably you heard about Great Pacific Garbage Patch. And it's not everything what we are producing. In chemical and pharmaceutical industry, to produce 1 kilogram of chemical substance, let's say 1 kilogram of not very sophisticated drugs, average amount of chemical waste which is generated is 100 kilograms. So the question is, can we continue like that, or we should improve ourselves? Our recent emergency situation with COVID-19 pandemic showed us that indeed we need drugs. Indeed, we need all of these polymers to produce gloves, to produce single-use syringes. And our population increase, so we need to produce more. But how we should produce this? Can we continue like that? We should produce more, but produce better. By better, I mean with using less energy, because producing polymers in good quality requires a lot of energy, and also generating in the same processes less amount of chemical waste. What I need to tell you is that chemical reaction required energy. It's not like, reaction just happen. Otherwise, we will just implode, because our bodies are kind of specific chemical factories which are under catalytic control. And when you would like to go home, which is just after hill, you need to use energy. You need to climb up. But if you would like to go faster, easier, with less energy and in shorter time, you can use specific tunnel. And this specific tunnel leads you directly in front of your doorstep, not to the nearest bus station, not to your neighbor's home, just direct in front of your home. And that's the beauty and magic of the catalysis. Catalysis helps us decrease amount of energy which is required in the reaction, and also help us to minimize amount of chemical waste. And this magic ingredient, catalyst, it's not used in this reaction. After reaction, we can use this catalyst again and again and again and again. Nowadays, our very efficient catalysts are based on precious metal. They are very efficient, they allow us to produce a lot of polymers. But after reaction, their chemical waste are quite toxic for our environment. Also, these metals are in limited deposits, and usually these deposits are located in countries with unstable political situation. In my research, I would like to propose some exchange. I'm designing catalysts based on earth-abundant metals. Earth-abundant metals are much more available in earth crust than precious metal. Also, in their chemical forms, they are less toxic. And particularly, I would like to focus on iron. Iron is relatively non-toxic. Iron ores are everywhere around the globe. Iron is everywhere around the globe. Also, iron is in our bodies, so it couldn't be so toxic. We have around 4 grams of iron in our body. And to design and investigate this catalyst based on iron, I'm using computational chemistry. Computational chemistry is a branch of chemistry which allows us to solve complex chemical problems using computational simulation. And in my research, I'm using high-performing computers where quantum mechanics theory is implemented in specific software, and based on that, I'm able to observe what is happening during reaction. For example, for this kind of specific catalytic reaction, for 3 different catalysts, we know only starting point and the final product. Using computational chemistry, I'm able to check what is happening inside, what is the structure of particular intermediates, which electronic properties affects reactivity, and how we can improve this catalyst to make and work this molecule better. And based on this knowledge, collect all of this data, at the end of the day, I'm able to create specific guideline, kind of traffic signs which help us to, based on electronic properties of this molecule, on their magnetic response as well as their structure, to choose the best one from a lot of others molecule and synthesize only the best candidates. We don't need to synthesize, for example, 50 molecules. We can synthesize at the end only the best one. Only the 3 best one. And using this approach, we are able to save our time. We can save a lot of energy. We can generate much less chemical waste because we are focused only on the best shots. And last word, we know that we need chemistry for our everyday life. We simply need everything around us. But I think that in chemistry, there is a lot of place to improve ourselves. There is a lot of things we can improve to make our future better and make chemistry more environmentally friendly. Thank you so much for your attention, and I would love to answer a question.
Thank you for a very interesting talk. I have one question. You mentioned that catalysis helps minimizing chemical waste. Can you explain how do you reduce chemical waste with catalysis?
Thank you for this question. Actually, it's a very good question, because using catalysis, we can get much higher yield of product than we normally would get without that. So, for example, without catalyst, we can produce 5 kilograms, and rest will be chemical waste. And with catalysis, we can get 10 kilograms of product and only 1 kilogram of chemical waste.
Thank you.
Thank you.
Hi, Monika from Weizmann. Really nice talk, Kasia. I was wondering about the other side. So with your tools, with your computational tools, can you actually design some chemicals that help then to degrade the plastic that is accumulating? Not making the process more efficient, but maybe the degradation more efficient, so that with these tools also this problem can be tackled?
Yes, thank you. Actually, it is possible because, like, for example, to produce polymers, we are using catalysis. Also to degrade or change their chemical form, we also using catalyst. So let's say that we can design particular structures which can help us in recycle to all of them. Like, for example, it's not only because in catalysis we will change one chemical form to another. So it's not a problem to take plastic as our substrate, not our product, and change this plastic to, okay, now we can change this to another plastic. It's only one way, but we can make this chemical waste more easy to storage.
Slava from Weizmann. Have you thought to build some maybe protein scaffold around your accessible elements? So maybe you can delegate the degradation or synthesis to really biologically available. It will make it even more ecological, I think.
Thank you. You're right. There is some research in this field where people are using bacteria to decompose the plastic. But I'm not from biological side. I'm from chemical side, and I think that will be hard to connect bacteria with this catalyst which are based on metal. Because the thing is that sometimes. Okay, please continue, because I think that you would like to add something or not.
No, continue.
Okay. Because in my approach, I'm considering only this from chemical point of view. I know that there are biological processes which help us in recycling, but I'm not in this research. I'm not in this group, let's say.
What else? Thank you very much, Kasia.
Thank you.